Okay, so welcome back to the course vibration. I will continue the lecture from last week, the two degree of freedom model problem. So last week you have made modeling on your own, and I hope you can all get the answer like this equation. And so from this equation, we denote the matrix M by capital M and this matrix by capital C and this matrix by capital K, and the fourth vector is denoted by capital P. So the compact form of the equation looks like this: H double dot plus C H dot plus K H equal to P, right? And so what is the order of this equation of motion? Second order? Second? No, fourth. Fourth order, because you can see this is second derivative, but each state H has two components. So that's why this is fourth order, not second. But anyway, for ordinary differential equation or ordinary system of differential equation, the solution has the form of exponential or trigonometric. But in this case, because um, we consider the case that the the root of characteristic equation has complex number, then the exponential form can be uh, s- represented by trigonometric function like cosine. So we take this form, this general solution. um, then we take the time derivative. H, this one is H, capital H, and then we find H dot equal to something I can write down here. H dot should be omega times A1 A2. Derivative cosine should be uh, minus sine omega t minus phi, right? And then find H double dot. It must be minus omega square A1 A2 cosine omega t minus phi. Then substitute this back to this equation. Not really this equation, but the homogeneous equation. This one actually. Then we can simplify into this form. Okay. So you can see we have stiffness K1, K2, um, and also M1 and M2. Oh, let me point out this part. First, we consider a zero damping, which means C equal to zero. Okay, that's why you don't see appear here. And that's why we can write the general solution as purely trigonometric. There's no exponential form at all because the equation we are considering now is h double dot plus kh equal to 0, right? Yeah, this equation. So h dot here, h double here, substitute yeah, substitute here, and h, this one in here. Then I think I can write down fully for you. Yeah, so I will write in another page. So get h double dot is, yes, h is a1 a2 cosine omega t minus phi, and then h double dot is minus omega square a1 a2 cosine omega t minus phi, right? Then m times h double dot plus k times h equal to m1 m2, h double dot is minus omega square a1 a2 and cosine omega t minus phi plus uh, a1 a2 k, sorry, matrix k, matrix k, what is k? K1 plus k2 minus k2 minus k2 k, all right, k2 time a1 a2 cosine omega t minus phi equal to 0. Then you simplify, yeah, take cosine as a factor, so something here, and then cosine omega t minus phi equal to 0, which means this equal to 0, right? Then you got this term, okay? So when you get here, uh, then think about how we can find a1 and a2. If you have a square matrix time of vector a1 a2 equal to 0, if one person say, well, a1 equal to 0, a2 equal to 0, that's a not interesting solution. Of course, if h equal to 0, it must satisfy this equation, but that's not vibration, right? H equal to 0 is just stay there. um, the interesting solution is, what are the value of a1 and a2 which are not 0 and satisfy this equation? So do you have any idea? So this say characteristic polynomial, yeah, set the determinant to be 0. So why? I can review a little bit. Um, Let me just call this matrix is capital calligraph like this. So m times a1 a2, okay, m times a1 a2 equal to 0. That's what it say here. So I just say this is m, okay, and so m times a1 a2 equal to 0. And let me give example. So what kind of matrix M that can make this multiplication 0? Let's choose A1 as 1 minus 1, simple one. And the element M here can be, if I choose this one, um, let's say this is 2. Let me choose here is H, and here is 2H. Do you think this can be 0? 0, right? Yeah, 2h minus 2h, 0. And here, what can you choose here? Well, I might choose um, 2y, and here must be 4y, right? Then I got here 0. Then you observe here, what does this look like? You have you have a vector h and 2y, and then you have a vector 2h and 4y. What do you think about these two vectors? They are parallel, right? They're parallel. So if they are parallel, they cannot form the whole space. The whole space is 2 by 2, which means in the plane. But if they are parallel, they are form only a line. So it means this matrix does not have full rank. Okay? Does not have full rank, which means determinant of this matrix that I call it M calligraph must be 0. Okay. So in order to solve this equation, we take determinant and set it to 0. Then you have the equation of variable omega. Yes, of course, variable omega, because when we choose solution here, we do not know what omega is yet, right? So from this equation, we can find omega. Uh, yeah, first we find omega square 1, 2 equal to this using normal, yes, big omega square here, square like this, and then omega square here. So it's just like second order polynomial equation in terms of omega square, right? So we have two positive root for omega square. Am I correct? Yes, two positive root. And then we find omega, we can have four roots, right? This is because it's four order. That's why you can get the four roots. But here, here lambda is called eigenvalue. You recall the eigenvalue problem? If you recall it, let's say, yeah, I want to find the eigenvalue of matrix M, or let's say this, yeah, eigenvalue of matrix M, eigenvalues time eigenvector equal to, sorry, the matrix time eigenvector equal to eigenvalue times the eigenvector. Okay, and you can write like this, v minus lambda v equal to 0. Then take v, uh, the factor v as a factor, and then can have m minus lambda, because this one is scalar. Then you need, in order to have operation with matrix M, you need identity, because v time identity will be the same, it will still be, right? So this is 0. Then you can see that this looks like this equation, right? And the eigenvalue for this equation is omega square, where eigenvalue of this definition is lambda. Okay, that's why lambda is called lambda equal to omega square. Here is eigenvalue of this problem. Okay, and yeah, now we got two eigenvalues. So for After we got eigenvalue, we can find eigenvector. Look, okay. So, I th- yeah, in special case, when we choose k1, k2 equal to k, m1 and m2 equal to m, okay, same spring, same mass, m1, m2, then eigenvalue can be reduced to this term, some coefficient times this ratio for lambda 1, and some a constant this constant time this ratio for the lambda 2, right? Now we only have parameter k and m. Then frequency can be found like this, period like this, okay? And then we can look at the mode shape of vibration. Um, there are two mode shape because we got two eigenvalue, okay? Um, so how do we find this mode shape? Um, the first mode shape we find the ratio between a1 and a2 and a1. The amplitude of a1 is the amplitude of the vibration for each one. Right? If you get back to the general solution, a1 is amplitude of h1 and a2 is amplitude of h2. So we want to see the ratio between the two amplitude. Okay, and the ratio can have two different shape. That this one is called mode shape one. Yeah, the first mode shape. And how can we have this ratio? How can we get this? If you get back to this equation, uh, you can just time a1 times this and plus a2 times this and equal to 0, right? And then you can find the ratio between a1 and a2, right? From this equation. What about this equation? Can you do the same thing? You then, yes, you can use it. But actually, this vector and this vector are parallel. Either you use the first equation or the second equation, you will get the same ratio, right? Because they are dependent. That's why determinant is 0. So yeah, I can recall, I can review for you a little bit. When you see a matrix that have either column vector dependent or row vector dependent, the same because rank of column and rank of row are the same. Okay. So when I say the first column vector and the second vector are dependent, and then I say the first row vector and the second row vector are dependent, yeah, of course, always true, right? Um, so the two different mode shape is because of the two different value of omega square. For this one, the omega square equal to this time k over m. But when we find the ratio, k over m cancel out, right? And this is for the second mode shape. And this figure is just a brief illustration of the mode shape. This means you discretize. I think this graph should be a discretization. Here is the ratio of the magnitude. Um, look, it should be it should be yeah, this is one represent this one, and this value uh, it means if you choose one for amplitude a1, then you got this value as an amplitude of a2, okay? So it's kind of like this one a2 and this is a1, okay, something like that. And similarly for this one, the amplitude Okay. Here, if this is A1 and then this is A2, something like that. Okay. And another interesting property is that the two eigenvectors are orthogonal. Why? Yeah. Why these two eigenvectors are orthogonal? Very interesting. And how to check the orthogonality between these two eigenvectors? Just find the dot product. So 1 times 1 equal 1. 1.618 times minus 0.618 supposed to be 1, right? Let me check. Yeah, 1.618 times 0.618. Yes, almost 1 because we truncate some decimal of the value, this value. But why they are orthogonal? Because the matrix M is symmetric. When you have symmetric matrix, all column of eigenvector are orthogonal each other. Okay. Yeah, it can be proved easily in algebra, but I'm not going to do that. Um, okay, for the next part, undamped free vibration. Again, an undamped means we do not have the matrix C from the damper, right? And so the equations still look the same form. Uh, yeah, this one is for homogeneous solution. Okay, yeah, omega n refer to natural frequency. So because we have two different omega, then we can have the solution in this form. The sum of uh, the solution with omega 1 and the solution with omega 2, right? Then for any set of initial condition, um, yeah, for any set of condition, we can find C1 and C2. Okay, we already know the amplitude, we already know omega 1 and omega 2. Then using initial condition, we can find C1 and C2. Okay, in initial condition, because our equation is uh, like this plus kh equal to 0. Second order with respect to capital H. Okay, so we have two initial condition with respect to capital H, which is like this, and yeah, okay. Because for the free vibration, there's no external force, so of course you must have some value of initial condition. It's like you pull out the two mass to a certain h1 and h2, and then you release it, then it has motion. Okay, this one can be zero, that's fine. Oh yeah, either one of them can be zero, but at least one of them must not zero for the free vibration. Otherwise, the general solution would be just equal to zeros. Okay. Um, yeah, for the initial condition, if you look at here, you can say it's only two equations, but actually no, this one This one two equation, and this one also two equation. And you have four parameter: C1, phi1, C2, phi2. So from this four equation, then you can find C1, C2, phi1, and phi2. Okay. Any question? Any question up to this point? Okay, if no, then I move to the next part, which is example one. So example one, given initial condition velocity is zero, velocity of h of m1 and m2. Here instead of capital H, yeah, this slide use small h. And initial position is delta and 1.618 delta. And this say there's no phase angle since initial velocity is zero. Yeah, this is a little bit not obvious. Okay, it is not very obvious, but you can check whether this is true or not. If you choose the form of equation like this, you say a1 no, not use a. What other? Let's say alpha cosine omega t plus beta cosine sine omega t. If you choose this form, it can be easily checked whether this statement true or not. Because velocity zero means uh, you want to find the velocity. This one becomes sine. This one become cosine. Okay, and cosine at initial time at time zero is one. If this is one, it means beta must be zero. That's why finally you only have this form of solution. Yeah, you can do it more detailed to check it. Okay, so now the solution is in this form: C1 cos amplitude times cosine, C2 the mode shape 2 times cosine omega 2, and then use this initial condition, these two initial conditions to find C1 and C2. Okay, so actually C1 is delta and C2 is zero. C2 is 0. So when if we start from the initial position like this, but we see a line of the amplitude A1 and A2, so the vibration only have one shape like this. Okay, because C2 is already zero. C2 is zero. So yeah, this is the illustration of the amplitude of A1 delta here, and then A2 here. Okay, this is A1, if A1 here and then A2 here, something like that. Okay, and at particular angle, particular time, which means omega t equal to pi over 2, then both H1 and H2 has zero magnitude like this. Okay, so can you understand, get this illustration? Because A1 and A2 are the amplitude of H1 and H2, and they vibrate, right? Vibrate like that. And the ratio between these two amplitudes always 1.61h, something like that. Okay, so yeah, oscillate something like that. This one is high, this one even higher like that. Okay. Any question? Sri Hong, any question? No. All good. Example two. Um, yeah, now both modes are involved. If you choose initial H1 and H2 to be 1 delta and 2 delta. Okay. So following the same process to find initial or to find C1 and C2 using initial condition, which means using initial displacement, then you can get the C1 and C2 like this. So the final answer, the final solution of the motion H1 and H2 take this form. Okay. So H1 and H2 are the combination of cosine omega 1t and cosine omega 2t, right? Then if you want to see the wave, how the waveform look like, you can simulate it. Okay. And of course, you can simulate using numerical method or analytical method because you already have analytical solution here. Okay. Um, the next part is about transformation of coordinates. Um, so the original equation for undamped free vibration, this one, and let's say we choose another variable, yeah, two other variables z1 and z2 like this. Okay. Z1 and Z2 actually is the, what do you call it, how much you stretch or you squeeze the spring in between M1 and M2, something like that. Okay, and then substitute this back into this equation. We can have another equation in terms of Z1 and Z2. But here we can see that we can have another form which is uh, which have a interesting property. For the spring part, we can have a matrix which is uncoupled. But here we have initially coupled for the matrix M. Okay. So each one is how much you stretch or ski spring one, and H2 is how much you ski or stretch spring two. That's why you have uncoupled spring mass. Okay, Stephen, you can say the matrix of spring stiffness. This is one way of transforming coordinates. Another general form of transforming coordinate is to use eigenvector transformation. Okay, let me recall what you just saw. Um, we have found that we can select coordinates so that first initially coupled. Initially coupled mean this one. Yeah, if initially coupled, elastically uncoupled. Yeah, uncoupled, which means this one. Or initially uncoupled, elastically coupled, which is the original equation. Initially uncoupled, but elastically coupled, right? Then, big question: can we select on it so that both are uncoupled? Both are uncoupled means we can have a diagonal matrix times uh, other variable. Let's say you call it other variable. So we already have h and z. Let's say y. Okay, y1 double dot, y2 double dot, and then you have another diagonal matrix for y1 and y2 like this. It means uncoupled for both matrices. In this way, it's easier to find a solution, right? You can have just say a1 y1 double dot plus b1 y1 equal to 0, and then you have a2 y2 double dot plus b2 y2 equal to 0. So you can independently solve the equations. It's much easier, right? So this is the big question. How can we select coordinate systems so that both are uncoupled? Yeah, I give a hint, but I won't explain every detail in here. Just give a hint. Because is full range matrix, diagonal matrix, and all elements are non-zero, we can rewrite equation as h double dot plus m inverse times k h equal to 0, right? So can we choose a matrix U such that U time we have matrix U such that y equal to U H, and then or H is equal to U inverse time Y, H double dot equal to U inverse Y double dot, and then substitute into this equation U inverse Y plus inverse k, u inverse y equal to 0. And then this can be reduced to just uh, y dot plus some diagonal matrix y equal to 0. Okay. So can we have this kind of nice matrix U? Yeah. This is the goal. So what U should look like? Okay. All right. Now you can take a break for 15 minutes.